So welcome everyone. Thank you very much for joining our ECE Data Science Distinguished webinar. Before presenting our speaker today, let me briefly go over some logistics. If you have any questions, you can write them in the Q&A chat. And towards the end of the talk, we are going to select some of those questions to be answered by our speaker. During the talk, I'll also monitor the Q&A in case there's any pressing clarification question that makes sense to address in the middle of the talk. Otherwise, we're going to address most of those questions towards the end. The talk will also be recorded and uploaded to our YouTube channel for future access. So that being said, it is my pleasure to present today Professor Nikos Sidiropoulos as our distinguished speaker for the data science seminar. Originally from Thessaloniki, Greece, where he did his bachelor's, Professor Sidiropoulos later earned his PhD in EE from the University of Maryland, College Park in '92. He has served on the faculty of the University of Virginia, University of Minnesota, and the Technical University of Crete in Greece prior to his current appointment as chair of PCE at the University of Virginia. Yesterday, actually, when going over your CV in more detail, Nikos, I noticed that you had this kind of palindromic faculty career. So let's say UVA, Minnesota, Crete, Minnesota, UVA. So I found that quite interesting. So his research interests are in signal processing, communications, optimization, tensor decomposition, and factor analysis, with applications in machine learning and communications. Professor Sidiropoulos received numerous awards, of which I just handpicked a few to list here. He received the NSF Career Award in '98, the IEEE SPS Best Paper Award in 2001, 7, and 11, the IEEE Signal Processing Society Meritorious Service Award in 2010, and the Distinguished Alumni Award from the University of Maryland in 2013. He's also a fellow of both IEEE and EURASIP and very involved with these professional organizations. On the personal side, even though we have not collaborated yet, we have plenty of collaborators and friends in common. Nikos is a world-class expert in tensor methods for signal processing, among other things, and his work is certainly my go-to reference on this topic. Actually, so whenever I read or review a paper on tensors and I start seeing all this wacky notation with different kind of tensor decompositions, and I go with the, with the chicken feet there with my fingers trying to understand it, I am actually jealous of Nico. And I actually think, oh, I'm sure Nikos can understand this on his sleep. So Nikos, thank you for agreeing to spend the afternoon with us here today. It is great to have you, and the floor is all yours.
Thank you so much, Santiago. That's very kind of you. Thank you for the invitation. It's a great opportunity to talk about some of our latest work that we're excited about. Yes, indeed, I am sort of a palindrome, which is, in Greek, it is synonymous in a way to regression. And since I'm doing a lot of regression, right, that's appropriate. So let me say that this is joint work with my PhD student, Nikos Kargas, who is finishing up his PhD at the University of Minnesota, where I used to be up until a bit less than 3 years ago. And we're going to talk today about what I think is a principled alternative to neural networks. I'll talk about the methodology and its applications and try to convince you that there is a lot of interesting work in this area for guys that have a signals and systems background, like many of us do. So let me, go to my slides. Okay. So today I'm going to talk about what is known as the supervised learning problem, right? And this is one of the core learning paradigms in the machine learning community. And what the way you think of this problem is you have a certain unknown nonlinear function, f, that maps inputs to outputs. And you observe essentially pairs of inputs and outputs. And you're trying to figure out what is the function in between. So this is the classical setting in which we train, for example, neural networks for classification, but in which case the output y is binary or categorical, right? But there are also situations wherein the output y is real valued when we're trying to do prediction or regression, since we're talking about regression. Or even complex valued if you are trying to predict, for example, a missing sample in MRI case space or baseband equivalent channel tap in a wireless communication setting, right? So this is the sort of general supervised learning problem, and you're sitting there, and you're scratching your head, and you're asking, how can I figure out what this F is? In signals and systems, which is my pedigree, this is also known as nonlinear system identification. So that's another, nonlinear function identification. System is usually reserved when you have dynamics. Actually, this framework can incorporate dynamics, but I'm not going to go into that right now. But in this case, typically, Y is real valued or complex valued, right? But otherwise, the setting of the problem is the same. So what is the sort of the state of the art nowadays for dealing with nonlinear function identification or nonlinear system identification or supervised learning? This is deep neural networks. It is the most popular method that we have today for essentially learning how to mimic nonlinear functions. There is a little bit of theory behind neural networks, but for the most part, we don't really understand when they work well and why they work so well when they do. Choosing the right architecture is often an art with a few exceptions. So we know a lot now about images. Convolutional neural networks are doing a great job there. But in many other cases, when we have categorical data, for example, it's very hard to choose the architecture. Furthermore, even if they are able to learn, it is hard to prove that they learn, especially from a finite set of input-output samples. And that's a major drawback, right? It's hard to prove that they learn, and it's hard to interpret them because you have sort of this maze of potential connections without a real meaning associated to each connection. In a way, if you are trained in signals and systems and in theory, and the way that many of us were trained, the success of deep neural networks is kind of against odds and principles, against the book. So in this talk, what I would like to talk about is a more principled alternative, which is based on what I call tensor principal components. It is based on tensor decomposition, which is, as Santiago said, is one of my areas of long-term interest. I've been working in this area for 25 years now. And this is sort of the basis of the modeling approach that we will take, although there's a lot more to it. The approach that I will be talking about has several advantages. It is intuitive if you understand the concept of low-rank modeling. It is universal in that there is very little that we assume about the nonlinear function. It is interpretable because it is unique and because we can use the latent modeling part to say something about the operator. And it is backed by theory. An important advantage relative to neural networks is also that it works with incomplete input data. To make this a bit clearer, you train a neural network to take a certain input vector and output a certain output, right? But if 70% of the elements of this input vector are missing for a particular case of inputs, this is clearly impossible, right? Whereas our method naturally handles this important case. All right. So we're dealing here with a general nonlinear function identification problem. It is a supervised setting. And we are wondering, what can we say about identifiability? So under what conditions I can identify the nonlinear functions, right, of interest, nonlinear function, performance and complexity issues. So in many cases, let me see, if the function is linear, then we know everything about this problem, right? The question becomes more interesting when the function is nonlinear. What can we say about identifiability, performance, and complexity? Obviously, this has a wealth of applications in machine learning, systems and control, wireless communications, you name it. So just to flash a few motivating applications, one of the problems we have considered over the last several years is in the area of learning data analytics, and in particular, the problem of predicting a student's grade in a course before the student actually takes that course. So this can be viewed as a recommender system problem or a collaborative filtering problem when you have historical data about students in the department or in the college, as well as the previous grades of a given student, you can think of this problem as making a prediction is like making a prediction about the rating, right? And you can use collaborative filtering tools. So that's an important problem because it helps us better guide the students, better advise the students, detect early problems like potential for dropping out of the program and things like that. So we had a joint grant with one of my colleagues in Minnesota, George Karipis, for several years, and we worked with real data. We'll show you some results. Another problem of interest is drug response prediction. So you have patients, possibly health signs, genomic data. You have also historical data about other patients having the same or similar diseases, and you'd like to predict how a drug will work in that particular patient. Problems like topic mining and text classification, they can be put in this context. Problems in wireless channel estimation and prediction can be put in this context. I've always maintained activity in this area. So a lot of the problems that we tackle can be put in this quite general framework. All right, so I will cut through the chase now and give you the basic idea, right? Before I do that, I wanted to give you a very, very brief overview of tensors and low-rank tensor decomposition. So first of all, what is an n-way tensor? What is a three-way tensor? It is a data set. You can think of it as a data set. You can also think of it as an operator. But let's think of it for the moment as a data set that is indexed by 3 or more indices. What is a matrix? A data set that is indexed by 2 indices, row index and column index, right? So a three-way tensor is indexed by 3 indices. A higher weight tensor is indexed by more than 3 indices, right? Now, you know that a rank 1 matrix is the outer product of 2 vectors. A rank 1 tensor is the outer product of 3 or more than 3 vectors, depending on the order of the tensor, right? So what you see here in the chicken feet is a rank 1 tensor, right? A1 outer product, A11 outer product, A12 outer product, A13. And what you see here, the summation of these rank 1 tensors is a decomposition of the tensor X in rank 1 tensors. The smallest number of chicken outer feet, chicken feet outer products that you need to decompose a given tensor in this way is called the rank of a tensor. And it is actually the same for matrices. The smallest number of outer products that I need in order to synthesize a given matrix is the rank of the matrix. The difference with matrices is that there is a row rank, which is the number of linearly independent rows, and a column rank, number of linearly independent columns, and all 3 definitions of rank coincide for matrices. For tensors, they don't, right? And the right generalization of rank is what is the minimum number of rank 1 tensors that I need to decompose the given tensor. There are many ways of writing down this decomposition, and I'm not going to spend much time on this because it takes time to absorb. But the important thing to remember is that unlike matrices, for which low-rank decomposition is non-unique because of the possibility of rotating the low-rank factors, matrix factors, for tensors, this is no longer the case. And under generally mild conditions, low-rank decomposition of tensors is unique. And this is something that on which I've spent many years of my professional life. So let us talk now about nonlinear function modeling. How can we use tensors to model nonlinear functions? There has been work in this area, in particular on the problem of modeling polynomial functions. So let us go first to the very left of this figure, where you see the inner product of a weight vector and a vector x of unknowns, right? So that's a linear function of the vector x. So every linear function of a scalar linear function of a vector x can be described by another vector W containing the combination coefficients. What about a quadratic function? So a quadratic function of a vector x can be written as this quadratic form, and this quadratic form involves a matrix of coefficients W, right? So I can describe any quadratic function of the vector x in this way, x transpose wx, and what I need to specify is this interaction matrix W, right? Now, if I want to include linear functions in addition to homogeneous quadratic, if I want to include linear functions, all I have to do is stick a unit at the bottom of vector x, right? And in this way, I actually create linear terms as well, and I can model everything, right? So once you understand this, it is not difficult to see how you can model third-degree polynomials, multivariate polynomials, right? So for third-degree multivariate polynomials, what you really have is a form which involves 3 instances of the vector x, right? And the 3-way tensor of coefficients, right? So this is the rightmost figure. So mathematically, we write this as W being the tensor of coefficients, right? Which is multiplied in the first mode by vector x, in the second mode by vector x, and in the third mode by vector x. So left, top, and right. This way, especially if I stick a unit at the bottom of vector x, I can describe any function, any multivariate polynomial of degree up to 3. Now, this is actually what Rendel has done in 2010, and there have been many followers since. He proposed doing this, but there is a complication, right? What is the complication? So here on the very right, I'm modeling a polynomial of degree 3, multivariate polynomial of degree 3, but the number of coefficients that I need blows up exponentially in the degree, right? So I need essentially a number of coefficients which is to the power d. That means that I cannot really do it for high orders or even medium orders because I hit the curse of dimensionality, right? In addition to this, I need to know, I need to have an idea about the polynomial order before any analysis, right? So this I have to live with, the prior knowledge of polynomial order, and I will have to stay with relatively small orders, but there is something I can do to actually alleviate the curse of dimensionality, and this is I can assume a model for the coefficient tensor W. So instead of leaving it unrestricted, I can say, let's say tensor W is a rank 1 tensor. Then the number of parameters grows linearly with D. In fact, if I have any fixed finite rank, the number of parameters grows linearly with D. But nevertheless, I cannot model high degree polynomials. So this approach has been tried about 10 years ago, and it didn't really manage to beat neural networks. So here comes now the essence of what I'd like to propose today. I will explain it with just one figure, right? So suppose for the sake of argument that I'm trying to learn a function of 3 variables. Let's call them x1, x2, x3. So there's a function f of x1, x2, x3 that I'm trying to find out, and I'm given input-output pairs, right, for this function. Now, let's make the simplifying assumption that the input variables are, in fact, finite alphabet. If they are not, I can always quantize, and I can do other things as well that I will tell you later. But for the sake of understanding, let's assume they are already quantized, right? Let's say each one of them takes 1 of 10 values. Every time I present you with an input-output example, right, I essentially give you a sample of a 3-way tensor. So when I give you that f of x11, x21, x31 is y1, what I'm telling you is that go to position x11, x21, x31 of that tensor and plug in the value y1. As I give you more input-output pairs, you fill in more entries of that tensor. Now this, of course, you can visualize when I'm talking about 3 inputs, but what happens if I have 2,000 inputs? The answer is nothing changes, of course. All we know about tensor theory right, carries over to 2000 way tensors. And even though up to our work recently, nobody has ever thought of using 2000 way tensors because everybody was working with 3 or 4 way tensors, right? All the theory and all the methods carry over, right? So the only difference is that in practical supervised learning problems, you have, maybe 2000 way tensors, right? Whose elements are indexed by many indices, right? But you can still play the same game. And then the question of how you generalize is, given a new point which you haven't seen, x1L, x2L, x3L on the right, you are querying to find out what is the value of the tensor at that particular point, right? So if you adopt this very simple viewpoint, what is the general nonlinear system identification problem? Very higher way, very high order tensor completion, right? Very simple idea. Now, what are the claims behind this idea? This was presented, by the way, AAAI this past winter, first paper in this series. So what are the claims behind this? First of all, we know that using a low-rank model, canonical Polyadic decomposition, in fact, you can model any nonlinearity, even of infinite order for high enough rank. Even for very low ranks, like rank 2, for example, it can be easily shown that a low-rank model can model highly nonlinear operators, and I will give you examples, right? So you can do very discontinuous operators this way. No other method that I know can do discontinuous operators. You can prove correct nonlinear system identification from finite samples when a tensor is low rank. In fact, you can have identifiability results. And even when the actual operator is not low rank, right? Take my picture, right? Take a picture of me, take the SVD, keep the 20 strongest singular components, discard the rest, reconstruct it, will still look like me, right? So even though nothing in life is low rank, everything in life can pretty much be approximated as low rank. So that's a very basic idea. And what we do then in this case, if the operator is not low rank and we use a low rank model, is essentially we are identifying the principal components of that nonlinear operator. Let me give you some examples to convince you. So suppose that you have a separable function, right? Suppose that the function of interest is the product of the signs of the inputs. It's hard to get something that is more nonlinear than that. But that model actually is a rank 1 model. So I can model any separable function of the inputs in this way, and it is just a rank 1 tensor, which is very easy to estimate, in terms of sample complexity and things like that. What about more general functions, right? What if I have a sum of separable functions? Then it can be shown that the rank is again very low, right? You can take it even further. You can think about functions that can be decomposed as sums of potentials over cliques, which is the sum of pairwise functions that I have on the third line down here. And again, this is a very low rank tensor, right? So any function in this class corresponds to a very low rank tensor in our model, right? So the rank of the latter is in squared over 2. I is the finite alphabet. N is the number of dimensions of the input variables, and the maximal rank is of the order I to the power capital N minus 1. So that's a very, very low rank model. All right, so how do you actually do it? Because theory is good and talk is good, but how do you do it in practice? That's not very difficult. All you need to do is essentially algorithms for tensor decomposition and tensor completion, right? So you essentially formulate a least squares problem. So you have a model for your tensor. This model, I will call it calligraphic X, right? And this calligraphic X is what you see on the lowest equation, the bottom equation on the screen. It is basically a low rank model of your tensor, right? And every time you have an input-output pair in your training, you say that I want my tensor at point xm1, xmn, right, to be equal to ym. And then you have a least squares criterion, which you can augment and you can constrain in various ways. One thing you can do is you can include, for example, Frobenius norm regularization on the low rank matrix factors, and that helps control the rank and improve generalization. And the other thing you can do is that there are many real life data sets which involve ordinal variables, have the property, the functions, right? Real life functions have the property that they are relatively smooth, right? So you may have actually, the framework allows modeling discontinuous functions, but most functions in practice will be smooth, right? And then you can actually encourage smoothness by introducing additional regularization terms that essentially take approximations of first order derivatives. This is appropriate for ordinal predictors, but not categorical predictors, right? Which have no sense of proximity or order. Okay. What can we say about, under what conditions can we identify a general nonlinear operator, assuming it can be modeled by a low rank operator from a finite set of input-output samples, right? So there are many results that one can apply because tensors have been around for many years and many of us have worked in this area. They are split in two categories. There are deterministic results. The most pertinent ones for our formulation are by Sorensen and De La Fauer in 2019. This is a fiber sampling approach and then a regular sampling approach by my other PhD student, Karylos Kanatsoulis. And then there are probabilistic results. And I'm not gonna spend time on the details there. You're welcome to take a look at the papers and I'll be happy to share my slides. So which result is appropriate? It depends on how the input samples are generated, whether they are generated randomly or systematically, and if randomly from which distribution. So we have good results in this area, but not yet optimal, let's say. We have a lot of work to do, but we can prove identifiability from finite samples if the rank is low enough. Let me leave you with this message. How do you do it in practice? So there are a number of ways to do it. You can exploit sparsity. You can do alternating optimization. You can actually do stochastic gradient descent, log stochastic gradient descent for reduced variance. A lot of algorithms are applicable. For smaller problem instances, we do essentially alternating optimization. For larger problem instances, we resort to SGD. One of the claims I made early in the talk was that we can handle missing data. And when I say missing data, of course, in tensor completion, you have tons of missing data, but that's not the kind of missing data that I'm talking about here. I'm talking missing data in the predictors, right? So I would normally give you, let's say, a vector of 200 elements, right, to predict this patient's drug response. But hey, I'm missing his genomic response. I'm missing his cholesterol. I'm missing this and I'm missing that. I may be missing 70% of the input data, right? This is the same as saying that I'm missing indices in our formulation, right? How do you handle that? Other methods, including neural networks, have no obvious way of doing this. And what you can do perhaps is take the mean value of a certain missing attribute and sort of plug it in place. But our approach allows actually a very nice marginalization. So if we have a simple model, in this case, just an independent rank 1 joint PMF model of the distribution of the predictors, then we can use that to average out the tensor modes and marginalize, in a way, computing the average response over all the possible values of the missing variables And it actually turns out that this can be done in a computationally very efficient manner. So the formula is down here. So what we are doing is we essentially, when we don't have certain input variables, maybe a lot input variables, right? What we do is we compute a conditional expectation, right? Based on a simple, may I say simplistic, joint probability model for all the missing variables. And again, the details can be found in this paper from AAAI 2020. All right. When we do regression in particular, as well as classification in some cases, we are interested in multi-output regression, meaning that we are trying to predict multiple variables at the same time from the same set of predictors. And there are two ways to go about doing this. One is to build independent models, and the other is to build a joint model with essentially with multiple outputs, right? And we usually prefer to take the second approach because these output variables are usually strongly correlated. So our model can handle this as well, and all it takes is augmenting our tensor with one more mode or one more way. So if it is 1,000 input variables, right, and we want 5 outputs, we will have essentially a 1,001 way tensor, right? And that is the matrix V, right? That is induced by the matrix V in the model, which you can estimate together with every other matrix if you are doing alternating least squares or stochastic gradient, right? So that's another sort of facility or side benefit of our approach. We can actually do multi-output regression simultaneously. So all this is nice and good, and theory and excitement is good, but at the end of the day, what matters is how well something works in practice. So I'd like to show you real results with real data, and these include both some standard data sets from the UCI repository and data for grade prediction from the University of Minnesota, from that NSF project that I was talking about earlier, right? So we have 9 data sets from the UCI repository and this grade prediction task. For the grade prediction task, we chose to predict grades in computer science courses from the University of Minnesota. I have given different earlier versions of this talk a few times, and I've been asked why computer science and not electrical and computer engineering. The answer is that computer science is harder to predict. ECE is a relatively easier task for a variety of reasons. So in all our simulations, we split our data into 80% that is used for training and 20% that is used for testing, and we take the training part, the 80%, and do 5-fold cross-validation for the parameter selection. So all our parameters are chosen through cross-validation. There is no magic number here, right? Everything is chosen through cross-validation. And we evaluate the performance using root mean squared error. Talking about parameters, how many parameters do we have? You know, when you design a neural network, you have to decide, you know, how many layers, hidden layers, how many nodes per layer, things like that. What is the nonlinearity? Is it a ReLU or what else is it, right? So there are many choices. Here we basically have one parameter. The basic parameter is 1, and it is the rank of the tensor that is modeling the nonlinear function. That's the single most important parameter. In a way, our approach in that sense is closer to being non-parametric. The other parameter is the smoothness regularization penalty and the rank penalty. So you may have from one parameter, which is key, and it is the rank, to maybe up to 3 parameters. That's all, right? So I'm showing you here some details about the data set. These are from the UCI repository, and the number of variables is relatively small here. I will take you to higher numbers later. So the number of variables is 18, for example, for Skillcraft master table, 19 for Parkinson's telemonitoring. The output is ordinal or mixed as shown here, and the ranges are provided. For the grade prediction task, we have a number of data sets, 20 different data sets. The N is 34. M is the number of input-output pairs, and you will notice that these are very few, right? So we are trying to learn a general nonlinear function of 34 input variables, and the number of examples we are given here is about 900. That's all, right? That's a challenging problem, right? Most of these are challenging problems. So what are we using for baselines for comparison, right? So we have ridge regression, support vector regression, using decision trees, and a neural network regression. This neural network in particular is a multi-layer perceptron, right? So we have ridge regression, support vector regression, SVR, DT, MLP, and our method is at the very end. And what we saw here is root mean squared error plus or minus standard deviation. So you see, for example, for the energy efficiency task, support vector regression gives you 2.68 in RMSE. Decision tree gives you 0.56, so big improvement, right? The neural network gives you 0.48, and our method gives you 0.39. For energy efficiency 2, likewise, you look at SVR, it's 3 versus approximately 1 for the neural network versus 0.57 for our method, CSID, right? Canonical system identification. There are several data sets, There are several data sets here. There are some in which our method is not the top. For example, abalone, you will see that both SVR and the neural network do slightly better than our method, but we are close, right? 209 versus 223. So the general Parkinson's disease is also very interesting. Most methods, simple methods, do 7.5 in RMSE. A decision tree does 2.4. Neural network 3.6. Our method 1.33. So significant improvement. So either our method is the best or it is close to being the best. And it is a very generic method without need to choose a kernel or anything like that. So these experiments were with full data. If we randomly hide 30% of the input data and we use the mean or the mode for imputation for the baselines, of course, every method is worse than when you have full access to the input data, but our method remains the best, right? And again, has significant improvements, except for this one, this red one, by sharing, where we actually are doing third, I think, yes, after decision trees and multi-layer perceptron. And all these experiments have been optimized so that we give every benefit of a doubt to every other method. So every method is carefully optimized. Similar results when you have multi-output regression, but I will skip that. We do really good work there as well. Let me talk about grade prediction. And this is a difficult problem. The reason it is a difficult problem is that, first of all, you can predict using the student's essentially GPA or a combination of the student's GPA and the class average, historical class average for that particular instructor, let's say. And you can do a reasonable job this way, and then you can add, sophisticated recommender system methods and prediction methods, and they will give you some improvement, but not very significant, right? So let's look, for example, at the kinds of improvements that are possible, right? So look at the left panel here. If you use the GPA, you get something like 0.43 for CSI 5. If you use the best method in the literature for this problem right now, you get the same result. If you use our method, you get a slight improvement. There are other data sets like CSI 6, for example, where you can get a more significant improvement, 0.63, 0.57, right? There are a few cases where you can get a more significant improvement, but generally speaking, this is a data set where it is hard to get very significant improvement. One of those good examples on the right, top right of the screen, data set CSI 12. GPA gives you 0.58 in terms of root mean squared error. Biased matrix factorization 0.51. Canonical system identification 0.48. So that's, relative to the GPA, that's a significant improvement. Okay. So we talked about canonical identification of multivariate functions, and I'd like to take a sort of a breath at this point and do a recap. So we talked about general nonlinear system identification as tensor completion. In fact, if you take my viewpoint, at least for discrete inputs, right, for finite alphabet inputs, nonlinear system identification is very high order tensor completion. They are equivalent, right? Low-rank models, as I explained earlier, for tensors can model highly nonlinear functions, including functions of infinite degree, nonlinearity degree. And even if they are not, the actual function is not low rank, you can still aim to identify its principal components, which from an engineering point of view makes a hell of a lot of sense, right? But the question that comes to mind is, what about continuous inputs? So a lot of the problems we deal with in practice, the inputs are continuous, ordinal and continuous. An obvious way to address this is to quantize. But there is an inherent trade-off in such quantization, and the trade-off is, if you do it very coarsely, you have low resolution, and therefore poor generalization. And if you do very fine quantization, you have very high computational complexity in this approach. And you also have very few data samples, and then again, you are overfitting, right? So if you do it too coarse or too fine, you have bad performance, basically, right? You can tune it, and it is not very difficult to tune it, but one wonders whether there is an alternative approach that can overcome this altogether. So at this point, this is sort of where I take off my machine learning hat and I put on my signal processing hat. And the solution that we came up with, and it was very, very satisfying, goes back to what is arguably the father of signal processing, which is Jean-Baptiste Fourier. And the idea is quite simple, right? So let me try to explain it. So suppose you have a one-dimensional function, right? A function of one variable x. Let us suppose that this function, we are interested in this function only within a finite support, right? Let us restrict the domain of this function to be 0, 1. If it is of finite support, and every practical function that we will ever care about in engineering will be, essentially the inputs will be bounded, right? I can always shift and scale and put them into 0, 1, right? And this is a reversible transformation. So I'm considering an arbitrary function on 0, 1, right? And I can essentially use a Fourier series to describe it, right? I can do a cosine, I can do a sine, I can do or both, right? But I can do a Fourier series. And we know a lot about Fourier series, right? So for example, if the function is sufficiently differentiable, right? It is in CP, right? Then the Fourier series coefficients are guaranteed to decay at a certain rate. And this will allow me to truncate the Fourier series and guarantee a certain approximation, right? Depending on how smooth or how differentiable the function is, right? So every function that is compactly supported or periodic can be represented using a Fourier series. And the nice thing about this is that this Fourier series for all practical functions decays, right? The coefficients decay, so I can truncate the Fourier series. And what have I accomplished? I have accomplished a way to turn an infinite dimensional problem essentially into a finite dimensional one, right? So this is the basic idea, and it carries over to the multivariate case. If I have a function of 1,000 variables, right, I can use multi-dimensional, 1,000-dimensional Fourier series, right? And I can write the Fourier series representation, and under differentiability conditions, I will have the decay of the coefficients, and I will be able to truncate the Fourier series, right? And what I managed to do in this way is turn a problem which has continuous variables into a problem that has discrete variables, the multivariate Fourier series coefficients in the Fourier series domain, which I can further make a finite tensor by truncation, and this will incur controllable error depending on how I truncate my tensor, right? There are many interesting things about using Fourier series in this context. One of them is that you can have a very natural estimator for the coefficients, which I have down here. If the input samples are drawn independently from the hypercube, right, then you can easily show that the natural estimator for the Fourier series coefficients is the sample average at the bottom of this page. All right. What are the challenges associated with such a very, very, very high order multivariate Fourier series? Of course, that the number of coefficients grows exponentially. And there is also large variance of the estimates when the number of examples you have is small, right? But I can control, essentially, the complexity of this model by introducing a low-rank model for the Fourier series tensor, right? So I introduce a low-rank model for the multidimensional Fourier series, not for the raw tensor, the data themselves, but for the Fourier series representation, right? So in this way, you get a low-rank model of this coefficient tensor, and what you can see, what you can show is that if you take a Fourier series approach and you truncate it in the Fourier domain, what this means, if you go back to the time domain, right, is that you model multivariate functions, right, as a finite sum of outer products. In other words, a finite sum of separable functions. Okay, how do you fit this model? There are two basic ways to do it. The first way is to go back to this estimator of the multivariate Fourier series coefficients. You can estimate these coefficients. You can even estimate the variance in those coefficients, and then you can do a direct fitting approach in the Fourier series domain. And that's one approach. We will call it FSA-LR. And the other is to fit the coefficients directly on the training data without going through the Fourier series. Now, this is conceptually more complicated, but computationally and from a performance point of view, actually works better, right? So we will mostly use this hidden tensor factorization approach in which you fit the coefficients directly on the training data, minimizing squared error between the observed and the predicted response. Okay, so we will refer to the second approach as FSA-HTF. HTF stands for hidden tensor factorization because you actually do not observe directly, right, the elements of the tensor that you are trying to fit. Okay, as an engineer, I always like to try something in simulations first, because before I take it to real data. And so what we have simulated here is sort of two extreme cases. One nonlinear function that is itself a simple neural network model, and one nonlinear function which is not a neural network model, but it is low rank, right? So what we see here in experiment 1, right? You have 4 figures, so top left figure. In experiment 1, the true function is low rank. It has rank 3, and its univariate function that we take the outer products is a linear combination of 2 Gaussians, right? So what you see here in purple is our approach, how well it learns mean squared error as a function of SNR on the top left, and mean squared error is a function of training samples on the top right. And the green one is a neural network approach. And you will see that we are learning better in this case than the neural network approach. And the reason is that it is in our ballpark, right? It's a low rank multivariate function. The bottom case is the opposite. it is actually a function generated by a neural network with a single hidden layer. And you will see that the neural network is the green again. The neural network approach is doing very well, and we are almost on top of it in terms of performance, both as a function of SNR and as a function of samples. So that's a sanity check. Before we get to real data, and again, these are data from the UCI repository, and what you will see here is a lot of the original methods, neural network, decision tree, our canonical system identification approach with quantized inputs, and the latest one with the hidden tensor factorization using multivariate Fourier series without any quantization, right? And as you can expect, it actually improves things. Look at WE2, the third data set, for example. Look what support vector regression is doing, 7.36. The neural network is doing 2.03. Our old approach is doing 0.34 with quantization. The new approach with Fourier series, 0.24, right? So you've gone down by more than an order of magnitude relative to simpler methods, including the neural network, right? An order of magnitude better than the neural network. Okay, so I'll skip the other details here because I want to leave a few minutes for questions. So what is the punchline here? What did I tell you about? We talked about nonlinear system identification or supervised learning, or learning a general nonlinear function from the viewpoint of tensors, and in particular as an instance or of very high order tensor completion. One of the benefits of this is that you get provably correct nonlinear identification under low rank conditions. So you can prove that you do it correctly. Low rank models can model highly nonlinear functions, including infinite order nonlinearities. And even if the actual function is not low rank, then what you claim here is that you identify the principal components of the nonlinear mapping, which makes a lot of sense from an engineering intuition point of view, much more than training an unstructured neural network, in my mind. What is coming up in this line of work? We have ensemble versions. This will appear in Asilomar 2020. So far, I talked to you about a non-parametric approach. Essentially, the only parameter is rank. The question is, what if we know something about f of x? And there's work under review on this question. And there are other tensor models that one can pursue. So with this, I'd like to stop. Thank you for your time. Thank you for your attention. And I'll be very happy to answer any questions that you may have.
Great. Thank you, Nikos. Thanks a lot for the talk. Yeah, so we're open here for questions. So, okay, so actually the question we have posted here, so one had to do with the first discussion that we're having about actual conference talks. So here someone asked in the middle if these are discretized identification methods. However, towards the end, you actually talked about alternatives to avoid discretization. So I think this is answered. So let me actually start with just a simple question here, just to motivate the rest while they're typing. So when you talked about missing data, right, that you marginalize, those missing features, I missed. Is this something that you can only do during testing, or you can also train with this sort of missing data? I think I missed.
You can train with missing data.
You can train with missing data.
In fact, those results are with missing in training and missing in testing.
Mm-hmm. Okay.
And it's the same principle in both cases.
Right. Mm-hmm. So, so when I was listening to this, right? So in the let's say this idea of machine learning and kind of a layered architecture kind of mindset, right? Which of course here you're trying to move away from it. What if someone comes and say, okay, since you have these tensors from which you can have the output can be multidimensional, I can just grab that output. It's a multidimensional, and then pass it through another tensor of size, however dimensions you have in there, yes, with some sort of non-linearity in the middle or something like that, right? So would that be too crazy? Would that be completely unnecessary? Have you guys even tried something like that?
Yes, we have tried something like that, and this is the Asilomar 2020 paper, okay, which is essentially boosting, right? So what you're doing is you have one stage and you use it to predict, you train it to predict, then you take the residuals, right? And you try to predict from the residuals, right? So you can have actually a chain of such learners, if you wish, or several parallel ones, and then combine them either in parallel concatenation or in serial concatenation. So yes, and this, to answer your question, yes, this helps.
This helps, right?
This helps in certain cases, not always, right? But it helps in certain cases. Yes.
Then, yeah. So since we don't have, so the when you talk about when you have this continuous setting and they say, okay, let me just look at the let me make, let's say, periodize this function if it is finite support, so that then I can go to a Fourier series domain. I can truncate the coefficients, and even I can further think about the tensor of coefficients itself being low rank, right?
Right.
So you briefly touched upon what this is implying about the underlying function. But would you mind spending like an extra minute or so giving a bit more of flesh into that?
Yes, absolutely. Let me go back to my. So essentially, if you look at equation 1, I have to move my video to come. Give me a second here because it overlaps the equations. Right. So if you look at, where is equation 1? Yes. So if you look at equation 1, right? So if you these AK coefficients, right, are your Fourier series coefficients, right? So if you take this low rank model for the Fourier series coefficient tensor and you plug it in here and you do some derivations, what turns out is that what you are modeling then is that the general multivariate function, right, is modeled as a sum of R terms. R is the rank of the Fourier series tensor. And each one of the functions inside the sum is an outer product, right? So you have a product of F1R x1, Fnr xn. So you have a product of continuous functions, right? So you have a separable multivariate function, right? So by truncating the Fourier series and assuming rank R for the Fourier series tensor, right? The equivalent model back in the time domain is that you model a multivariate function, which is, it has to have, it has to be differentiable so that you can truncate the Fourier series. You're modeling a multivariate function as a sum of outer products or a sum of separable functions, right? So this is the insight that you get. Now, you can easily say that let me take spherical Gaussians, right? I can spherical Gaussians are separable, right? And you know that if you give me any function, right, and I have enough Gaussian functions, right, I can approximate it, right? That's why sort of Gaussian mixtures can approximate everything, right? But the issue here is that you allow a lot more flexibility, right? Because these separable functions can be themselves comprising multiple Gaussians, right? So they can be any separable functions, right? So that's the idea. But that's the sort of the bottom line. So it was not clear, right? So this is, in a way, if you look at it, this equation, this is a generalization of canonical Polyadic decomposition from tensors to functions of continuous variables.
Yeah.
Such generalization, right, cannot be exact, right, in general, but because if you assume, differentiability up to a certain order, you can bound essentially the error in this approximation.
Mm-hmm.
Sounds good.
Sounds good. Thank you, Nikos. So, okay, so we are already at the mark of 2 p.m. So I think this is a good point to end the talk, and thank the speaker again. Thank you, Nikos, for joining. Let me remind everyone that this talk is being recorded, so it will be uploaded. If you wanna, go back and check some of the things, or if you know someone that couldn't make it and want to see this talk.
Thank you, Santiago. Thank you all for attending.